ADIF, through the construction companies Fomento Construcciones and Sando Construcciones, has entrusted Herrenknecht AG with the excavation of the Siete Aguas-Buñol tunnel for the high-speed train service to the Mediterranean city of Valencia. The project will employ the Herrenknecht double-shield 2373 UNAX, designed and manufactured in Germany specifically for this project. The TBM has a diameter of 9.72 meters and a total length of 370 meters. The Siete Aguas-Buñol project is part of the large-scale infrastructure project for the high-speed rail connection between Madrid and Valencia. The TBM from Herrenknecht will be used to excavate two 6,000-meter sections of the La Cabrera tunnel with a gradient of 3% in each of the two tubes. The project also includes the construction of another tunnel, two cut-and-cover tunnels, and two viaducts. In the first phase of the excavation, the geology is composed of micritic limestone and loamy limestone. Later, the second phase will bore through material consisting of dolomites, dolomitic limestone, and limestone. The double-shield TBM is considered the most technically sophisticated machine used in tunnel boring, flexible and easily adaptable to the changing geology of the excavation route, thanks to a support system combining grippers and the installation of tunnel lining segments in a synchronized process. This type of machine offers optimum safety standards and very high levels of productivity, able to advance 1.6 meters and install the tunnel lining in less than 30 minutes. In comparison, conventional boring machines with tunnel lining systems require twice the time for this distance. The experience gained in recent years by construction companies and the manufacturer has led to significant technical improvements. These include the apertures in the telescopic shield above and below, which permit compressed materials to be expelled during the regripping process and absorb the convergences of the ground. A foam processing unit for conditioning the ground. A perforation unit positioned behind the erector to contain the ground. Movable platforms between the first trailer and the shield for the injection of mortar through the third and fourth ring. Control of the excavated material using two scales and a metal detector. A geotechnical prediction system. The operating process of a double-shield TBM is described below. The operating process of a double-shield TBM is described below. As the TBM advances, it is protected by a shield which progressively secures the geological structure until the installation of the tunnel lining is complete. At the rear of the machine, the tail of the shield, prefabricated reinforced concrete segments are installed. These segments serve as a final single lining of the tunnel, ensuring the TBM and operating personnel inside are always protected. The shield pulls a system of trailers equipped with a control cabin and all the other components necessary to ensure the supply of electricity, water and air. The logistics of the segments and other materials for the lining of the tunnel must be closely synchronized and performed without delays in the trailer. The double-shield TBM owes its name to a particular design feature. The front part of the machine has the frontal shield, which moves forward. This shield permits the advance of the cutting wheel. The rear of the machine, behind this structure does not move during perforation. The resistance during perforation, torque, and longitudinal forces are transmitted to the geological structure through the grippers, footings which extend from the central body of the machine. As opposed to traditional TBMs, thanks to this detachment of resistance forces, the lining segments can be installed during the perforation process. This continuous perforation, that is, tunnel perforation and simultaneous construction of the tunnel lining, ensures optimum performance and productivity. In this case, the auxiliary propulsion cylinder's only function is to fix the lining segments as they are installed, and to advance the central body of the machine during the process of changing the position of the TBM. Once the position change process is concluded, the gripper footings are retracted and the rear part of the machine advances against the front shield of the TBM using the auxiliary propulsion cylinders. The position change process, called regripping, only takes a few minutes. At this moment, the machine is ready to continue advancing in the perforation. Continuous perforation is only possible in sections where there are no geological faults, as the grippers require a stable surface as a support base. If the double shield TBM reaches an area with geological faults, the front shield is retracted telescopically. In this case, the entire TBM is pushed forward using the auxiliary propulsion cylinders supported on the tunnel lining segments. This perforation method is called discontinuous perforation, as it can only continue with perforation using the propulsion cylinders once the segments of the tunnel lining are in place. This method of operation ensures maximum safety in unstable ground or where geological faults are present. Thus, the machine can adapt to the changing geological conditions and achieve optimum perforation efficiency under any conditions. This sophisticated process of continuous perforation using double shield technology requires complementary solutions in the assembly and mechanical characteristics of the TBM. The cutting wheel is powered by 14 frequency-controlled electric motors arranged in a ring. These are connected to the gears of the principal bearing of the cutting wheel through the individual gearboxes. TBM has cutting power of 4,900 kilowatts, supplied to the cutting wheel housed in the front shield through cylinders called torque box cylinders. Through the adjustment of the torque box cylinders, horizontally or vertically, the overlap of the cutting wheel and the shield is adjusted. This overlap is necessary to minimize the friction between the rock face and the shield, to compensate for the possible convergences of the rock face and permit the control of the TBM. The cutting wheel can also be displaced longitudinally using two cylinders able to adjust its position 600 mm. These cylinders are supported on the steel structure of the frontal shield, and the hydraulic housing of the entire unit ensures that the force exerted on the principal bearing is perfectly determined. This displacement of the cutting wheel can be useful when boring through solid rock face, for example, to free the cutting wheel from the face, or to create a space for work between the face and the wheel. The transmission of torque resulting from the perforation process and the advancing force necessary between the frontal shield and the gripper shield are aspects of key importance in the double shield TBM. The advancing force acting in a longitudinal direction is generated by the principal propulsion cylinders which join the frontal shield and the gripper shield. The torsion generated during the perforation process is transmitted to the gripper shield through the structure and the two torsion compensation cylinders. These cylinders compensate the movement relative to the frontal shield and the gripper shield. The grippers are housed, floating in the gripper shield. Two heavy hydraulic cylinders, located between the two footings, push the stabilizers outwards to the geological formation. The force of the advance and torsion are transmitted to the contact area between the gripper shield and the gripper footings. In this way, a forceful union is created between the gripper shield and the surrounding geological formation, and a definitive transmission of force. The cutting wheel of the double shield TBM is equipped with tools for the perforation of hard rock. 59 steel discs or cutters, with a diameter of 17 inches, are housed in the cutting wheel, turning against the tunnel face through the rotation of the cutting wheel. Each of the cutters exerts a force of 27 tons on the tunnel face, fragmenting the rock. The debris, in the form of rock chips, falls to the floor of the tunnel. This material is then captured through 12 apertures and conduits and carried upwards through the rotating movement. From there, the deflectors direct the debris to the center of the back of the cutting wheel, from where the feeder deposits it on the conveyor belt. The actual lining of the tunnel takes place at the rear part of the shield. A terminated section of the tunnel is formed by 6 prefabricated segments of reinforced concrete. Each segment is fitted with a waterproof seal around its perimeter to prevent groundwater from leaking into the tunnel. An erector is used to install the segments, controlled with a portable control unit used in direct visible contact. The segments are lifted from the feed mechanism in the rear, through which the erector is continuously provided with new segments. At the location where the segment will be positioned, the auxiliary propulsion cylinders are retracted before the new segment is installed. The segment is positioned and fixed to the structure, immediately pressured by the auxiliary propulsion cylinders. The 2 superior segments and the keystone have a lateral inclination of 15%. The keystone is not installed laterally, but introduced from directly behind. In this way, the tunnel ring is constructed and the tunnel is extended ring by ring.